Hi and welcome to part 6 of this video playlist about the preparation of pyridines. This video is about the preparation of pyridines by cycloaddition and rearrangement. These reactions are commercially less relevant than cyclocondensations, and most reported examples are just mechanistically intriguing laboratory curiosities. Some of them can, however, give access to pyridines which are difficult to prepare by other routes. The main disadvantages of cycloadditions are that isomeric mixtures are often obtained, that the products tend to have too many or wrong substituents at the wrong position, and the high price of starting materials or catalysts. I've sketched here some of the most common cycloaddition strategies that can be used to prepare pyridines. Alkynes can undergo heterodiels-Alder reaction with a number of heterodienes to yield first dihydropyridines and then pyridines by elimination or cycloreversion. Suitable heterodienes include various heteroarenes, but for the less reactive pyrimidines and pyrrazines, only intramolecular cycloadditions have been reported. Also, nitriles can be suitable starting materials to prepare pyridines by cycloaddition, for instance by reaction with alkynes or with butadienes. Then, olefins can yield pyridines by Diels-Alder reaction with eszadienes or oxazoles. I'll show you now some specific examples which I found realistic or mechanistically relevant. This here is an example of the reaction of a nitrile with an alkyne, catalyzed by a cobalt complex. The cycloaddition proceeded in water and gave a good yield of substituted pyridine. Concerted cycloadditions are very sensitive to polar and steric effects. Thus, best results are obtained when one reacting partner is electron deficient while the other one is electron rich. Here, the electrophilic ethoxycarbonyl cyanide reacted with two molecules of a simple aliphatic terminal alkyne in the presence of 2.5% of a rhodium complex. A mixture of two isomeric pyridines was obtained in high yield. This type of nitrile also yielded a pyridine upon reaction with methylpropionate and 5% of a ruthenium complex. The cycloaddition already proceeded at room temperature and gave one main regioisomer. Electron-deficient nitriles can sometimes also be converted into pyridines by reaction with butadienes, as shown here. In this example, an electron-rich diene was generated from an imine in the presence of butoxycarbonyl cyanide in refluxing xylene. A bicyclic pyridine resulted with high regioselectivity and in high yield. This is another example of nitrile to butadiene cycloaddition. As catalyst, 10% of a nickel-0 complex was used and the reaction required 48 hours at 130 degrees Celsius. Alkenes can be converted into pyridines by reaction with oximes of alpha-beta unsaturated aldehydes or ketones. In this example, 4% of a rhodium complex and 16% of silver acetate were required to bring about the cycloaddition. Vinyl acetate acted as synthetic equivalent of acetylene because after the cycloaddition, acetate was eliminated. Unlike the previous example, here an electron-rich eszadiene reacted with an electron-deficient alkene. No catalysts were required, and both the initial Diels-Alder product and the dihydropyridine intermediate were stable. Aromatization was achieved by treatment of the dihydropyridine with hydrogen peroxide in acetic acid. In this example, acrylonitrile reacted with another type of eszadiene, again without any catalyst, to yield a substituted 3-cyanopyridine. Many examples have been reported of the cycloaddition of oxazoles to electron-deficient alkenes. This can be a practical route to 3-hydroxypyridines, which are often tricky to prepare. Again, no catalysis was required here, only heating for 2 days without any solvent. The oxazoles required for this type of reaction can be prepared by dehydration of N-acyl alpha-amino acid esters, for instance with phosphorus pentoxide, as shown here. In this example, the triethylammonium salt of acrylic acid was the dienophile. The initially formed carboxylic acid decarboxylated, and the final product was a 2,6-dialkyl-3-hydroxypyridine. This is an example of the addition of phenylacetylene to an ester enene. First, a base-induced isomerization occurred, followed by thermal cycloaddition to the alkyne. Mostly one isomer was obtained. 2-oxazinones are another type of heteroarenes that, like oxazoles, can react as ester dienes with olefins or alkynes. Dichlorooxazinones can be prepared from cyanohydrines and oxalyl chloride, as shown here. These react cleanly and at moderate temperature with terminal alkynes to substituted 2,6-dichloropyridines. Also 1,2,4-triacenes can act as synthetic equivalents of ester dienes. Instead of carbon dioxide, nitrogen is eliminated upon cycloreversion of the first hetero-Diels-Alder product. In this example, norbornene, a particularly reactive alkene due to ring strain, reacted once and twice with a triazine. The resulting dihydropyridine could be dehydrogenated with DDQ to the corresponding pyridine. With trichlorotriazine, no such dehydrogenation was required, and a 2,6-dichloropyridine resulted directly by elimination of hydrogen chloride. Few examples have been reported of the ring expansion of pyrols to pyridines with the aid of halocarbines. In this recent example, chlorophenylcarbene was generated by heating a diacerine in acetonitrile in the presence of a substituted pyrrole. A mixture of 2 isomeric pyridines was obtained in high yield. Also, furanes can undergo ring expansion to pyridines. In this example, 2-aminomethylfurane was treated with chlorine and hypochlorite in water, first under acidic conditions and then at pH 12. A high yield of 2-chloro-3-hydroxypyridine resulted. Here are some more examples which you can also find in the description of this video. The next video of this playlist is about the nucleophilic amination and hydroxylation of pyridines, including the Chichibabin reaction. These reactions enable the preparation of 2-aminopyridines and pyridones from inexpensive starting materials and are mechanistically quite unique. See you then.